this first part of the numbers theory, we're going to review the multiples and divisibility first. So first of all, let's see what is multiple. So if we say that a number a is a multiple of b, if a equals b times some integer, for example, if I have a number a which is 4, I have another number which is 8, we can say 8 is a multiple of 4 because 8 can be written as 4 times 2, right? So it's the number 4 times another integer, right? So to generalize a little bit, we can say that the number a is a multiple of b if a can be written as the number b multiplying an integer n. So here this number n must be integer. Right, so basically this is simply the definition of multiples, or how we can tell that one number is a multiple of the other. So for example, so if we know that if both 147 and 357 are multiple of number 7, is the sum of these two numbers still a multiple of 7? Right, so this example, we actually have two parts. So first of all, this can be a known condition, but you can also validate if these two numbers first are multiple of 7s. So multiple of 7s means, for example, 147 must equals 7 times another integer n. Right? So how, if I can find, which means if I can find the value of n, then I'm confident to say that 147 is a multiple of 7. And how do I find this n? It's actually if I'm using 147 divided by 7, if the remainder is 0. In other words, if the division gives you a integer results, then which means this is a multiple. So you may already see this because 14 is 2 times 7, but let's start with the long division. So if I have 2 times 7, I got 14. I have 1 7 left, so 7. So which means 147, it equals to 7 times 21, right? And similarly, the other number 357, it's 7 times 5 times 7 is 35. 1 times 7 is 1, so it's 7 times 51. So this is just the first part, just validating if the first condition is true, and yes it is. So these two numbers 147 and 357 are both multiples of 7. Okay, then the question is whether the sum of these two numbers are still multiple of 7. So then let's write the sum first. Right, so if I plus these two numbers together, so 14, 9 plus 1 is 10, 3 by 1 and by another one's 5, so 504. So is 504 then a multiple of 7? I can again use the division to check whether the remainder is 0 or it gives you a integer solution, which is yes. Right, so it is 7 times 72. Right, 72 is an integer, so this shows that the sum of these two numbers, 504, is also a multiple of 7. Now, after seeing that, we can further extend this question a little bit. So sounds like if I know that two numbers are multiple of a certain number, then the sum of these two numbers should still be the multiple of the same number. So can we generalize this statement and prove it again? So to generalize this, let's say suppose I have two numbers R and S. They can be any number and they are multiples of 7. Then how about the sum of these two numbers, R plus S? Are they, or is this number still a multiple of 7? So first of all, because this question is being generalized, so there's no, it's not just one number, it can be any number that's multiple of 7. But if we go back to the definition, for example, if the number R is the multiple of 7, which means it can be written as 7 times another integer. Let's say this integer is n. And similarly, if the number s is a multiple of 7, which means the number s can be written as 7 times another integer m. Note here that because I don't know the actual value of r and s, it can be any value that multiple of 7, which means I'm just using a different notation for the other integer. But this doesn't mean that they cannot be the same. I mean, m can be the same as n, or m can be any number other than n. So this simply means m and n are any integers. And then what I want to check is I want to check the sum of these two. Are they still multiple of 7? So then first of all, r can be rewritten as 7 times n. And s can be rewritten as 7 times m. And then if I'm taking out the common factor of 7, it just redistributes multiplication over addition. Then it's 7 times n plus m. Now here we need to use a simple conclusion that the sum of two integers must still be an integer. If that is true, that is true, and if that is true, which means this outcome is equivalent to 7 times, I will just use another notation k, but again, that really this k means or k must be an integer. So then in this case, it fits back to the definition again. So this proves that the sum of these two numbers are still a multiple of 7. And then furthermore, it's this example is using a multiple of 7, but you can already see that I can extend this to, let me use a notation of a. So any number a or any multiple of a still fits this definition or fits this conclusion. Okay, so then let's see another example. What is the greatest three-digit number that is multiple of 13? the greatest three-digit number that is a multiple of 13. Right, so we're looking for a three-digit number, which is a multiple of 13, and we're looking at the largest three-digit number among all the possible outcomes. So three-digit number, maybe let's just start from the greatest three-digit number. So obviously, among all the three-digit number, the 999 is the greatest three-digit number. Let's just first forget about the multiples and other conditions, right? If we're just talking about three-digit number, this is the largest. So which means either this number is divisible by 13, then we already find the solution right away, or if this number is not divisible by 13, which means we need to move backward a little bit to move to the left-hand side of the number axis to find the next number which is divisible by 13. So then we don't have to start looking for it at the beginning. We can just check whether this can be divided by 13 right away, or if it cannot be, then what is the remainder, right? Because the remainder will tell you how much short or how much more than this division. So 13, first of all, I'm gonna multiple by 8 is not gonna be 8 is gonna be exceeded, so maybe try 7 first. So 21, 7 is 9, then I get 89, so which means must be 6, 18, 7, 11. So first of all, this number 999 is not divisible by 13 because you have a non-zero remainder, but the remainder hints you that I got 11 more than the number that's supposed to be divisible by 13, which means if I'm moving backward, moving to the left-hand side of the number axis by 11 steps, I can eliminate this number until it goes to 0, right? Like for example, so if this number is not 9 anymore, if this number is 8, my remainder becomes 0. This digit becomes 0. My remainder becomes 10. If this number further becomes 7, then my remainder will be 9, right? So if you're moving this to the left-hand side of the number axis, you will be able to eliminate the remainder at somewhere. And the original remainder of 11 hints you that you may need to move 11 steps. So we start from the greatest three-digit number. We subtract this extra remainder. We get 988. Then let's see if this number is good enough. I'm still going to multiply 7 first. You get 91, then 78. If I got a 6 here, 18, 7, and 0 remainder. So 988 times, equals 13 times 76, because 76 is an integer, so this number is a multiple of 13. And among all the three digits number, it is the biggest or the greatest number. There's another way to prove that this is greatest number, because the next multiple of 13 will be 13 times 77, right? If you want to looking for a bigger number. And this is also equivalent to adding another 3 onto this number. And this will give you, let's say 11, 9 plus 1 is 10, 9 plus 1 is 10. This will give you 1001, and this number is no longer a three-digit number. It is a four-digit number now, right? Okay, let's see another example. So how many integers between 150 and 300? How many integers between 150 to 300 are multiples of 9? Okay, so basically we're looking for multiple of 9s, but we're not just looking for random multiple of 9s, we're looking for multiple of lines that sits between this range from 150 to 300. So for example, you can of course just listing all the multiple of 9s. For example, you can start listing from 9. Actually, you can start from negative number, because negative 18, negative 9 are also multiple of 9s, right? Because we're saying that this n must be integer, but it could be positive and could be negative integer. So then you can keep listing all the multiple of 9s until you reach 300. So this is one way, but you can see obviously it's very time consuming. So is there going to be an easier way? So first of all, I'm able to find all the multiple of 9s between 0 to 300. And then if I can find all the multiple of 9s from 0 to 150, then the difference is what I'm looking for. How many integer between this region is a multiple of 9. So let's try in this way, because looking for it starting from 0 will make things a bit easier. So then what should we do? Again, like if starting from 0, the first number will be 9. Second number will be 18. The next number will be 27, 36. You can keep going. And then what is the last number, right? Because it looks like the key point is that I have no problem finding the number from the left-hand side of this interval, but what is the last number, or the last several numbers to the other side of this interval? Then this looks similar to the example that we just had. What is the largest multiple of 9 that is below 300? Right, so similarly, I want to check if this number 300 satisfies the condition right away. So I'm checking this first. So 300 is not a multiple of 9, because if you do the division, you have a remainder of 3, but then this remainder of 3 hints you that if my number is 297, if I'm using 300 minus 3, moving backward a little bit to get the next greatest number, this number is divisible by 9. Because if you use this divided by 9, you get 2, 3, 27, you get 33, right? Okay, so first of all, from 0 to 300, I have multiple of 9s can be listed in this way, and then the work is to count how many are they. Now is it similar, or do you recall that what we learned in the first lesson in arithmetic, that how to count how many numbers are there in a consecutive series, right? So here either you can use a way that because it's consecutive with the same step size, adding by 9 in this case, I can use the last term to subtract the first term divided by the step size and plus 1. I will get this 288 over 9 plus 1, 32 plus 1, so there are 33 numbers over here. This is one way. Another way, we can simplify this series. Up to here, I only want to know how many counts are there. If I divide 9 to each number, it changes the numbers, but it doesn't change the number of counts. So then this series will be converted to, if divided by 9 on each number, this will become 1, 2, 3, and the last number we just checked over here, it's 32, 33, and then this means we have 33 counts of numbers. Right, so now we get the first part done. Right, within this range from 100 to 300, I have 33 numbers who are multiple of 9. Then the second step, I also need to check the range from 0 to 150, and then after that we'll take the difference. Right, so this one I'm going to be a little bit fast. We still check whether this number is divisible or not. But divided by 9, 60, 54, remainder is 6, which means 150 minus 6 is 144, and 144 divided by 9 is 54. 6 times 9 is 54, so it's 16, right? So which means I have the series which is from 9, 18 until 150, 144. In other words, if I divide 9 on each number of that, I can convert my series to 1, 2, 3 until 16. So there are 16 counts. Right, so finally, I have 33 counts here, I have 16 counts here, which means between the range of 150 to 300, the counts is the difference, right? Or is subtracting this part from the bigger interval, and it gives you 17. So that's how we solve this question. So here already did a lot of divisions, and I probably already mentioned the word divisible many times. And as you can see, we're doing the division and we're checking whether the number is divisible by looking at the remainder. So looks like if the remainder is non-zero, we call it non-divisible. So how do we define this? So the divisible test is let A be any number and let B be non-zero number. Here actually the number A and B are in fact not even necessarily to be integer, but at the beginning you can still consider them or still start with your, for example, examples with integers only, but actually this can be extended to non-integers, and you will see from the conclusion that there will be an integer appeared in another places, and as long as your conclusion is an integer, then they are divisible. All right, so basically we only need a divided by b is an integer, then we can tell that a is divisible by b. So for example, use the example from the very beginning. If I have 8 divided by 4 equals 2, so then the number 8 is divisible by 4, right? Or for example, I have 297 divided by 9 equal to 33, then the 297 is divisible by 9. And in other words, if I have 300 divided by 9, I have 33 and the remainder of 3, then 300 is not divisible by 9, right? And then further extend the reason I'm saying that a and b are not even necessary to be integers, because for example, if I have a is 2.8, b is 1.4, a divided by b is 2.8 divided by 1.4, it's 2, right? Because simply if you multiply 2 on 1.4, you will get 2.8. So this also means 2.8 is divisible by 1.4, right? So you can see that this a and b not even necessary to be integers, as long as the division gives you an integer. As long as a divided by b is an integer, then these two numbers are divisible, like one number is divisible by the other one. Okay, let's see some more examples. Okay, for example, if I have a number 121212, this is in fact 121,212. So this number divisible by 3? Let's check. So there are different ways to check, and in fact the most basic way, if you write out the long division or just do the division, you will find that it is divisible by 3 by the end. But let me show a relatively easier way first, and then this will later conclude a even more easier way for you to use in the future. So first of all, this number, it has 6 digits. If you use this to divide by 3, you will need to do at least several steps of the calculations to get the final results. But what if I rewrite this number into 120,000 first, and then they're different, right? This has something more. You have 1,212 left, so 1,212. And then I'm writing as 1,200, which means I got another 12 left, right? So first of all, this number can be written in this way. And then besides all these zeros, the effective number that left out are all 12s. And we easily know that 12 is definitely divisible by 3. So which means this 3 numbers, each of them are divisible by 3. And remember the very first example we saw at the beginning, if the two numbers are divisible by 3, then the sum of two are still divisible by the same number. This is of course true for if you have 3 numbers, still true that if each one of them are divisible by 3, then the sum of the three numbers are also divisible by 3. You can keep checking by dividing this number by 3, you'll get 40,000, this will get 400, this will get 4. But you don't really have to write down all these numbers. You can stop here, and by looking at number of 12, you will see it's divisible. And then how about this? If I have another number which is 363,637, we can first, looks like the pattern is a little bit different in the last digit. So then if I'm looking at the same or the similar breakdown, and I know 36 is divisible by 3 because it equals 12. I know this is divisible by 3, this is divisible by 3, but this number 37 is clearly not divisible by 3, and in this way, which means the sum of the 3 numbers are not as long as there's one term that is not divisible by 3 or by a certain number, then the sum of these numbers is not divisible by this number, divisible by 3 in this question. You can also prove this. I will leave this for you to practice, but in fact you can, similar as the first example we saw in this lesson, you can generalize that conclusion first and then try to prove that why it is not divisible. If you prove that this component is not divisible, then this whole number is not divisible. After seeing the examples we had so far, you probably then want to ask, how can I check whether a number is divisible by another number? Is there a either way, or do I have to use a long division or whatever division to check the remainder first to tell whether a number is divisible? So if we do not learn any further patterns, then unfortunately that would be the only way from the definition that to check whether two numbers are divisible. But in the next few examples, we'll start from the example and we'll try to find some patterns, and then those will be the shortcuts for you to solve couple different special cases, and so that you can tell the divisibility in a easier way or in a much easier way. So the first one, how can we tell at a glance that a number is divisible by 10? Now imagine that if we can always start from writing some random examples of multiple 10. For example, 10 times 1 is 10, 10 times 2 is 20, the next is 30, 40 to 100. If you keep writing 110, you keep writing to 1000, for example, right? These are all the multiple of tens, of course we can have negative numbers, but they are all the same or the mirror of the positive numbers. So later on we'll just use positive numbers for example, but you just keep in mind that all these can be extended to negative numbers as well. Now go back to observing the random examples that I'm writing down. You probably already see the pattern, right? As long as a number is a multiple of 10, this number must have a 0 at the end of in its last digit or in the ones digit, right? So any number that I'm writing, I don't know, 2, 3, 4, 0, if I have a 0 by the end, and then if I want to divide this by 10, this is obviously just 2, 3, 4, right? Or any random number if the digits A, B, and 0. You can always get a integer solution. So this means any integer ends in 0 is a multiple of 10. Right, so this means once you're given a number, you don't really need to do a division. You can tell right away it is a multiple of 10 or it is not. For example, which means if a number that not ended with 0, 1, 2, 1, for example, if you divide this by 10, you will for sure get some remainders left. Right, so basically, this is true on both sides. So if you end in 0, you must be a multiple of 10. If you are not ends in 0, you must not be a multiple of 10. After seeing multiple of 10, how about multiple of 5? Because 5 seems can be extended as a special case from 5 can be extended as a special case from 10 because 10 is 2 times 5. We'll take a look at the 2 at a later time. So let's take a look at 5. Again, let's start from the same way, the same intuitive way that just simply write down random examples of multiple of 5s. I can keep writing as many as I want, but you probably already see the pattern here is that the last digit or the ending digit is keep changing between 5 and 0, 5 and 0, 5 and 0, and 5 and 0. Right, so the numbers ended with 0 is also a multiple of 10, and because 10 is 2 times 5, right? So which means 10 must also be a multiple of 5. We'll learn this, we'll summarize this at a later time, but here you already see, or you can already get a sense that if one number contains, or if the number 5 is the factor of 10, then the number that can be divisible by 10 must also be divisible by 5. And in fact also must be divisible by 2, because 2 and 5 are both factors of 10. But now go back to here. The pattern is that any integer ends in 0 or 5 is a multiple of 5. Is multiple of 5. Now let's check the other common number, multiple of 2. So I can still start writing the multiple of 2's. Right, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, then 12, 14 to 20, 22, 24. So you can see that, well, it's either the first one digit or more than one digit, but the last digit are repeating from 24680 24680, keep repeating. And these are all the one digit even number. So this concludes that any integer ends in 2, 4, 6, 8, 10 is multiple of 2. And this can be further extended because 2, 4, 6, 8, 0, these are all even numbers, or one digit even numbers. So which means this equivalent to say any even number is a multiple of 2. Okay, so we see the case of 2 and 5 and 10. Let's check other common numbers. For example, how about multiple of 9s? For this one, let me start with a example first, and then we will extend our conclusion from that example. So if I have a number 765, so first of all, this number divided by 9 will give you 8 by 9, 72, 45, 5 times 9 is 45, so it is divisible by 9. But because I want to generalize my conclusion should work in a general case, not only just for one example. So let's see what we can, or what can we conclude, or what can we generalize from this example. So first of all, I will try to use a similar way as one of the previous example we saw. That let me write apart this number in each digit, right? See, first of all, it's equivalent to rewrite this number as 700 plus 60 plus 5. But hundreds or tens are obviously not divisible, or not always divisible by 9, right? For example, 10 is definitely not divisible by 9. However, 9 is obviously divisible by 9. So if I get 9s from here, this means I'll get 1 left. But let's write in this way first, because this at least give you 2 components, and one of the components is guaranteed to be divisible by 9. Right? So at the beginning, I have 3 digits, so I can write it apart into 3 components with each digits in one number. And then for the digits that, for the numbers that has more than one digit, like the 3-digit number and 2-digit number, I can further write my tens or hundreds to be 9 plus 1 or 99 plus 1. If I have one more digits, if I have 1,000 digits, I can still rewrite this as 999 plus 1. So you can always write something of 99, 999 plus 1. So then if I'm going to just open the brackets, I have 7 times 99 plus 7 plus 6 was 9 plus another 6 and plus 5. And if I'm reordering this by put the 2 numbers multiplying by 9s together and the rest of the single digit number together. Then I have two groups of numbers, and the first group, because all the numbers are having a multiplying of 9 or 99 or something with 9, multiple of 9s, so this is guaranteed to be divisible by 9, right? I don't even need to be further writing it down. So then the question is whether this part is also divisible by 9. If it is divisible by 9, then the sum of the two numbers is also divisible. Remember the first example that we concluded. Or if the second number is not divisible by 9, then the sum of the two numbers will not be divisible. So we just check the second term. So 7 plus 6 plus 5 is 13 plus 5 is 18. 18 divided by 9 is 2. So this number is also divisible by 9. So the sum of these two numbers is divisible by 9. And here you can see that this means the first part with the 2-digit or 3-digit or 4-digit component can always be breaking down to two components with a single digit and with a multiple of 9s. And the multiple of 9s are always guaranteed to be divisible by 9, so they can be neglected. And which means we really just need to check the single or every single number from each digit. So the conclusion is that given any number, 2, 3, 4, for example, I don't need to do the division. I don't need to rewrite all these. I just check the sum of all the digits and to see if this is divisible by 9. And if it is divisible by 9, I know right away or at a glance that I know this number, this whole number is divisible by 9. Let's just check. 2 give you 18, 54, 6. So I just verified it works, right? I can give another example that probably not going to work. If I have this number, then the sum of all the digits give you 6, 10, 11, and 11 is obviously not divisible by 9, so then this number is not divisible by 9. Right, so then the conclusion is that if the sum of the digits is a multiple of 9, then this number is a multiple of 9. And otherwise, in this case, it is not a multiple of 9. So this will tell you a certain conclusion. Either it is divisible by 9 or it must not be divisible by 9. Okay, we have two more examples until we check all the commonly used single-digit divisor. So the next example, we just tested 9. So 3 can be concluded or can be derived in a very similar way. I'm using the same example here. I'm gonna fast forward a little bit because we already saw the same example. And the difference is starting from this step. So 99 can be further written as 33 times 3. 9 is 3 times 3. Right? Because as long as you have multiple of 9s, it must be a multiple of 3. We saw that when we compare the multiple of 10 and 5s. We will conclude that in shortly, but you will keep seeing such examples that if a number is divisible by a larger number, then it will definitely be divisible by this number's factor. So such that in this case, if this number is divisible by 9, and 9 can be written as 3 times 3, so then this number is also divisible by 3. So then I'm regrouping this by writing them into two groups. The first group are these two components that are proved or that are guaranteed they are divisible by 3, and then I have the leftover terms 7 plus 6 plus 5, right? And then I just want to check if this is divisible by 3. So the sum of that is 18. 18 divided by 3 is 6, so it is divisible by 3. And so that the sum of the digits, right? So this is very similar to the conclusion of multiple of 9. It's just instead of checking the sum of digits, it's multiple of 9. Here we check if the sum of the digits is a multiple of 3, then this number itself is a multiple of 3. Okay, lastly, we have checked 2, we checked 5, we checked 3, we checked 9 and 10. How about 4? Number 4 is also a commonly used number. So first of all, the number 4 is a factor from 100, right? But 4 is not a factor of 10, right? Because 10 divided by 4, it's 8 and with remainder of 2, right? So 4 is actually not a factor of 10, or in other words, 4 is not divisible by 10, but it is divisible by 100. So this means we can construct a similar example at 100 digits. So for example, if I have a number, so this would be 23,456. This number can be written as, now I'm isolating until the hundredth digit. So it's 23400 plus 56, right? Just isolate them into two parts, chopping from 100 digits. And then this first number is 234 times 100. And because 4 is a factor of 100, this can be further written as, right? So it doesn't matter what numbers are over here. This can be 234, this can be 345, this can be any number, as long as you have a factor of 4. It means this number, the first component of the number, this number must be divisible by 4, because you already have a factor of 4. So this means this part is okay. I just need to check the second part if this is divisible by 4. And if this is divisible by 4, then sum of the two numbers is also divisible by 4. and vice versa. If this is not divisible by 4, then the sum of the whole number is not divisible by 4. So 56, 4 is 1, 16 is 4, so it is divisible by 4. So in this example, then this number 23,456, it's a number that divisible by 4. And looking at this example, we can conclude that we have a way to check only the last 2 digits, right? Starting from the 100 digits, it is guaranteed to be multiple or divisible by 4, which means we only need to check the last 2 digits. So if the number formed by the last 2 digits is divisible by 4, then this number is divisible by 4. So basically you only need to check the last 2 digits, whether that number is divisible by 4. Right, so here we summarized some shortcuts by checking some commonly used number. For example, we checked 2, right? Every even number is divisible by 2. We checked 3, well, start from 0 and 1, 0 times anything is 0, right? 1 times anything is 1, is that number itself, or 1 is always divisible to any other number, right? So then for 2, we conclude that it's divisible for all even numbers. And for 3, we need to check the sum of all the digits to see whether this is divisible by 3. 4, we need to check the last 2 digits to see whether it is divisible by 4, right? And 5, we checked that last digit either 0 or 5. For 6, we haven't checked it because there's no simple conclusion for that. 7, also not checking this because there's no simple conclusion. 8, we haven't checked. 9, similar to 3, if the sum of the digits divisible by 9, then this whole number is divisible by 9. And 10, we checked. This we want the last digit to be 0, then it's divisible by 10. So we checked most of the first digit number with their divisibility. And here we have many shortcuts that can help you to determine the divisibility in a relatively easier way.